Hello everyone and welcome once again to my channel. In today's interesting mathematics class, I'm going to show you how to prove these three trigonometric identities. Without further ado, let's get down to business. The first one we have right here is tan to the power of 6x is equal to tan to the power of 4x multiplied by secant squared x minus tan squared x multiplied by secant squared x plus secant squared x minus 1. How do we solve this problem right now? The idea is to make sure that the left is equal to the right. And even for the second one here, we're also going to make sure that the left is equal to the right. And for the last one, we say that the left is equal to the right. We're going to show them in this video, and hopefully it's going to be very easy for you to understand. Now, whenever you're proving trig identities, there are things you ought to know. And what are those things? The first one is you should always start from the more complicated part. It's easier to simplify all you have on the right to this here than for you to expand all this into this. Okay? It's going to be very hard for you to expand tan 6x to everything we have on the right. So that's why it's always better for you to start with whatever you have on the more complicated part. That's how it is. The next thing you should also know is that it's always easier to work with sine and cosine than with tan, cotangent, cosecant, or whatever that you have out there. So that's it. And the third one is that you need to memorize these identities. There are a lot of them. We have the Pythagorean identities. We have the quotient identities. We have reciprocal. We have double angle. We have half angle. We have sum and difference. There are a couple of them, and you need to memorize them all because they might not be given to you by your lecturer in the examination room. Now, let's begin with the first one. So the first one that we have here, I'm going to draw a line. Okay. So the first question, this is our number one. I'm going to copy it down. So this question is tan to the power of 6 multiplied by x is equal to tan to the power of 4x. And we have attached to it secant squared x minus tan squared x secant squared x plus secant squared x minus 1. How do we solve this one right now? Okay, well, we're going to start from the more complicated part, like I said, which is the right-hand side. So I would say proof RHS. So this means I'm starting from the right-hand side. And with that, I'm going to copy it down. Let me copy it down. Here you have tan 4x secant squared x minus tan squared x secant squared x plus secant squared x minus 1. All right. Now, what do we do in this very case? How do we simplify this very expression right here? Remember that we have to end up with tan to the power of 6x. Now, if you look at this here, we have a secant squared x, we have another one here, and we have one more here. This means that secant squared x is found in almost, or is attached to almost every tan here. With that, I'm going to factor it out. I'm going to factor out secant squared x. If you factor out secant squared x here from the first one, if you remove this term with the secant squared x, what remains? You have tan 4x left minus, if you remove secant squared x from this again, you have tan squared x left. So you have tan squared x left. And if you factor out secant squared x from secant squared x, what remains is now a 1. You close the bracket, the negative 1 remains outside. So what we actually did here was when I factored it out, So secant squared x divided by secant squared x is a 1. Tan 4x times 1 gave us tan 4x. Now I factored it out again from here. Secant squared x divided by secant squared x gave us a 1. Tan squared x times 1 gave us the same thing. Now again, I factored it out from here. Secant squared x divided by secant squared x gave us a 1, which you see here. And then, because it ends here, I enclosed or ended the bracket here, and then the negative 1 remains outside. So what next do we do at this point? We need to remember that there is a Pythagorean identity that says if you have 1 plus tan squared x, this is equal to secant squared x. So you're actually going to be applying all these rules. You need to apply the laws, you need to apply the identities, you need to remember them. It's not something that you can just do. You have to memorize all those identities, and that's the most important thing. So here, we say that 1 plus tan squared x is equal to secant squared x. With this in view, we are simply going to replace this secant squared x that we have here with 1 plus tan squared x. So this means that wherever we see secant squared x, we are going to replace it with 1 plus tan squared x. So let's do that. Here now will now become 1 plus tan squared x multiplied by tan to the power of 4x minus tan to the power of 2x plus 1, and outside we have minus 1. All right, let's continue with this. So this is going to multiply the entire bracket. They are multiplying themselves. Remember that the secant squared was factored out from the original expression, which was this. So let's now multiply. This 1 will multiply everything here, and the tan squared x will also multiply everything in the same bracket. So let's quickly do that. Here we have a 1 multiplied by everything in the bracket. So it's going to be tan to the power of 4x minus tan squared x plus 1, close the bracket. And then we have the next bracket, which is plus tan. And here we have squared x. Okay, so it multiplies the tan to the power of 4x, okay, minus tan squared x. And then what next do you have? You have a plus 1. You close the bracket. Okay, so I'm going to enclose all of this inside the bracket. Okay, and then outside you have minus 1, which is the minus 1 that we also have here. Okay, so let's continue. 1 multiplied by tan 4x will give you tan 4x. 1 again times minus tan 2x will give you minus tan squared x. 1 again times 1 will give you plus 1. The next bracket we have tan squared x times tan to the power of 4x will give you plus tan 6x. Then tan squared x multiplied by minus tan squared x, you have minus tan to the power of 4x. Then lastly, tan squared x multiplied by 1 will give you plus tan squared x. We shall also enclose all this in the bracket. And outside we have minus 1. All right. Now let's simplify this. I'm going to rearrange this. Starting from the 6, I'll pick from 6, from 4, and then downwards. The first one we have here is a tan 6x. The next one is we have tan 4 to the power of x. The next one is minus tan to the power of 4x. And now we have tan 2x plus tan 2x. And this one is minus tan squared x. Okay, and here we have our plus 1. And outside the bracket, we have a -1. So I didn't change anything yet. I only rearranged them so that I'll be able to collect like terms and simplify the expression. Now, the next one right here that we have, okay, the next thing to do right here is to simplify. Now, if you look at this here, we have tan 4x minus tan 4x. They are like terms, just like you have, for example, let's say you have 2x minus 2x, okay? 2x minus 2x will give you a 0 because they are like terms. In the same way, tan 4x minus tan 4x will give you a 0, so you can cancel them. And the next one here, we have tan squared x minus tan squared x, okay? Tan squared x minus tan squared x is also a 0 because they're like terms, so we can cancel them out. And what now remains? Tan to the power of 6x. Here we have tan to the power of 6x, and we have a +1. And outside we have -1. Since there is a 1 here, an invisible one, so 1 multiplied by this will also give you the same value. We can now remove the bracket, and we now have tan to the power of 6x +1 -1. But we know that 1 minus 1 will give you a 0. What now remains is tan to the power of 6x. So we have tan to the power of 6x. And this now becomes our final solution. Remember where we started from? This was the original question that we had, where they said that we should show that either the left or that both the right and left are equal. So we have shown, we started from the right-hand side and we ended up with tan 6x, and that now becomes our final solution. Okay, now since we're done with the first one, we have to solve the second one. The second one here says that 1 plus cos 2 theta over sine 2 theta is equal to cotangent theta. 1 plus cos 2 theta over sine 2 theta is equal to cotangent theta. Let me do this on another page. The question here says, this is our second one, 1 plus cos 2 theta all over sine 2 theta is equal to cotangent theta. How do we solve this one right now? To solve this very problem, let's be correct. Let's ensure that we copied it correctly. 1 plus 2 cos 2 theta over sine 2 theta is equal to cotangent theta. Okay, now let's do that. Right here, we need to understand that we should always start from the more complicated part. In this case, the more complicated part is the left-hand side. So I'm going to begin from the left, and I will say proof LHS, or left-hand side. Then I'm going to copy down this. So here we have 1 plus cos 2 theta all over sine 2 theta. Now, we need to recall that we have a Pythagorean identity that says when you have sine squared theta plus cos squared theta, this is equal to 1. This is a Pythagorean identity, and you need to memorize this. It's really very important in your journey. But when it comes to proving trig identities, you can't do without memorizing these identities, right? This means that if this expression here is equal to 1, I'm going to replace everything here with sine squared theta plus cos squared theta. Okay, now let's do that. So we have sine squared theta plus cos squared theta plus the next one here, cos 2 theta all over sine 2 theta. Okay, so we also need to remember or to recall that if we have, for example, cos 2 theta, okay, like this one here, this is a cos 2 theta. We actually have to use a double angle formula. Cos 2 theta is equal to cos squared theta minus sine squared theta. You might ask me, where am I getting them from? This is actually an identity, and you need to memorize them. Okay, I memorize them. That's why it's quite easy for me. And with them, I'm able to recognize patterns. and solve these problems very, very quickly. You need to also do the same. It's really very important. So I'm going to replace this cos 2 theta here with cos squared theta minus sine squared theta, just like I did for the one I had initially. So this is now going to be, if I do the replacement, I'm going to have sine squared theta plus cos squared theta plus, remember here we now have all this is now going to become cos squared theta minus sine squared theta, okay, all over the denominator, which is sine 2 theta. Okay, now let's continue. If you look at the numerator right here, you will discover something. Here we have sine squared theta, and here we have minus sine squared theta, which means that they are like terms, right? If they are like terms, we can cancel them out. So sine squared theta minus sine squared theta will give you a 0. So we cancel them out. What now remains at the top? We have cos squared theta plus cos squared theta all over sine 2 theta. We also have to recall again that this denominator is also a double angle identity. That whenever you have, let me say, recall, whenever you have sine 2 theta, this is equal to 2 sine theta cos theta. Like I said, you need to memorize these identities. They are really very important. You cannot do without memorizing them. You need to memorize them. So if sine 2 theta is equal to 2 sine theta cos theta, that means that wherever we see sine 2 theta, we replace it with its equivalents, right? This is now going to be, at the top we have cos 2 theta plus, okay, cos squared theta plus cos squared theta will give you 2 cos squared theta, because they are the same, and since they're adding up, you now have 2 of them at the top, all over. At the denominator, we now have 2 sine theta cos theta, okay? 2 sine theta cos theta. Now, let's simplify. We have a 2 at the top and a 2 at the bottom. They can cancel out, right? Now, they can cancel out. And when they cancel out, what now remains? We have cos squared theta all over sine theta cos theta, okay? Now, let's simplify further. This cos squared theta can be written as cos theta, okay, times cos theta, okay, all over sine theta cos theta. I've not changed anything yet. Cos theta times cos theta will give you cos squared theta. It's just the same. So I split them up so that you understand when I start canceling them out, okay? Now, since they're multiplying, the cos theta on top can cancel out with the cos theta down, okay? So what now remains? What now remains will now become cos theta over sine theta. And we know that we have a quotient identity that says cotangent theta is equal to cos theta over sine theta. And with this right now, we're going to replace everything here with cotangent theta because that is what it is equal to. So this now simplifies to cotangent theta, and hence this is our solution. Remember that the question says that we should prove that 1 plus cos 2 theta over sine 2 theta is equal to cotangent theta. So we can now say, hence, shown. All right. Now we are done with the second one. Let's go ahead and prove the third one. The third one here says sine alpha plus beta in bracket minus sine alpha minus beta is equal to 2 cos alpha sine beta. How do we prove this one? Let's see what we can do about it. I'm going to copy this in the next page. Here we have the third one to be sine alpha plus beta minus sine alpha minus beta is equal to 2. Okay, let me try to get it. It's equal to 2 cos alpha sine beta. All right. 2 cos alpha sine beta. Okay, like I said, always begin from the more complicated parts, and we're going to say proof left hand side, okay, to indicate that we're starting from the left hand side, and we can copy it down. Here we have sine alpha plus beta minus sine alpha minus beta. Okay, now we have to understand that this is a sum and difference identity. Okay, so to simplify this expression right here, you need to know what we call sum and difference identity. Okay, they are really very important. And this sine alpha plus beta, so we say, recall, if you have sine alpha plus beta, sine alpha plus beta always is equal to sine alpha cos beta plus cos alpha sine beta. This identity has to be memorized by you. It is really very important. Okay? And then the next one is that sine alpha minus beta is equal to sine alpha cos beta minus cos alpha sine beta. Okay? These two sum and difference identities needs to be memorized by you if you want to really be able to simplify expressions or to prove expressions or identities like this. So we're going to show right now using these things, using these two identities right here, that sine alpha plus beta minus sine alpha minus beta, all in bracket, is equal to 2 cos alpha sine beta. Now we're going to replace them with their corresponding values. So for the first one, which is sine alpha plus beta in a bracket, is now going to be, let me begin from here. So we have sine alpha cos beta, okay? And here we have plus cos alpha sine beta, okay? Then we have minus, I'm going to open my bracket. I'm going to put everything here because this is my sine alpha minus beta. It now becomes sine alpha cos beta minus cos alpha sine beta. Okay? Since they are subtracting, I have to put them in the bracket. Now let's simplify. On the left, we have sine alpha cos beta plus cos alpha sine beta. I'm now going to distribute the negative across the first term and the second term. Okay, that's how to do it. So negative multiplied by sine alpha cos beta will give you minus sine alpha cos beta. Negative times negative will give you a plus. So here we now have plus cos alpha sine beta. Okay, so negative times sine alpha cos beta gave us a negative sine alpha cos beta. Now negative times negative cos alpha sine beta gave us a plus cos alpha sine beta. So let's simplify it further. I'm going to pick the sine alpha cos beta first, and then I'll pick finally the cos alpha sine beta. Let's do that. I'll pick this and this, and when I pick them, what do I get? Sine alpha cos beta minus sine alpha cos beta plus the first cos alpha sine beta here. We now have cos alpha sine beta, and the second one here plus cos alpha sine beta. Okay, now here we have sine alpha cos beta minus sine alpha cos beta, which means that they are like terms, and since they are subtracting, they can cancel out, they're equal to 0. And what now remains? We have cos beta, cos alpha